Okay, ready to go? Sorry. Okay, so what we're gonna do today is we're gonna finish the assembly instructions related to maintaining the stack and calling functions, and then we start a new lecture, which essentially is the main topic of today, which is calling conventions. So it's a assembly level conventions about how you call functions, pass arguments, return values, stuff like that, right? So again, we need it for, I mean, imagine you implement exec. In order to start executing main, you have to pass arguments on the stack, right? So that's essentially why we need to understand how the calling conventions are implemented to make sure that we can implement fork and exec system calls, right? Later on. So this is where we stopped last time. So I covered assembly instructions like arithmetic, logical operations. I covered control flow. We figured out how to compile something like if then else or a for loop. Doesn't seem too hard actually, but will be coming on the quiz, right? And now we're finally ready to start calling functions. So I keep asking a question. So what is stack? So who can tell me what is stack? Unexpected, okay.
It's an area of memory.
Area of memory, good. And how do we use it?
Well, it's a dedicated area of memory in the memory space that has a dedicated size. You grow, I think it is downward in one direction. You can only grow when you can't leave gaps in it, otherwise it gets through. And you just kind of grow one direction as you use it and you move it back as you use it.
Well, I mean, first of all, I'm impressed by how much detail you know. But roughly half of those details are, I cannot say wrong, but can be violated. And it's fun to understand how. So first of all, I agree with the first, with your classmate who said, okay, it's just an area of memory, which is pointed by the stack pointer register. It's not a dedicated area. It can be anywhere. And you as a developer, you can abuse it. You can put the stack pointer anywhere. So let's take a look, but let's start with this. So again, remember we have one special register, which is called instruction pointer. We already know what it does. The second special pointer, this stack pointer. It's a pointer which points to the area of memory. I somehow screwed it up many years ago, and I made this picture in such a manner that the 0 is at the top. Your classmate is right. The stack grows this way towards the lower addresses. On most architectures, it can be different, but on Intel it goes down, right? So it's this area of memory. It's not dedicated. It's just pointed by this, right? So you can change the stack pointer with any, like, how do you think you can change stack pointer? What instruction will you use? We know assembly beginnings. Add. You can use add. Exactly, you can use add and essentially ESP and any constant, like, because remember there's like a way to put a constant here. It can be a positive or a negative constant, right? So you can adjust it. Or you can use a move instruction and just load a constant into the stack register. And then what happens? Then suddenly your stack is here, right? You can do that. So in any of your C programs or any language, right? As long as you have access to the assembly instructions, you know, often languages provide this interface. You can just do that. If this interface is not available, you can allocate something large on a stack and still change the register, right? But let's keep it for later. So essentially, the high-level point here is that, you know, the area is somewhat special, but not really special. It can be changed, right? And we'll see as operating system designers and developers, we'll be changing the position of the stack. But it kind of serves, semantically, it serves a specific purpose. So if you change and suddenly like your stack pointer points to some obscure place, then your execution, most likely execution of your program will break, right? So in some cases, it's okay. So for example, last time we discussed coroutines, right? Or asynchronous, what do you call them? Asynchronous threads or something like that. Coroutines is a good word. So if your runtime implements coroutines, most likely that part which implements coroutines will be changing stack, because each coroutine will be executing on its own stack, right? The operating system might not be even aware of that, because the operating system think, okay, it's a one thread of execution. I will allocate one stack, but then internally the language runtime says, okay, well, I know that there will be a coroutine. Okay, how many people know what coroutines are? Yeah, it's okay. We will get back to this later in the class, not to coroutines, but some version of it. Let me just give you a brief example of what it might be. So imagine you have a piece of code which is something like this. Okay, sorry, let me just for, and imagine it's like goes for like 3, for example, like I++, right? And you do something like DNS lookup. And imagine that this function, DNS lookup, takes a lot of time, meaning you send a request on the network, and then half a second later or 100 milliseconds later, you get a reply from the network. And you say, look, then if I do it in a loop, I will be doing them sequentially. I get a request, sometime later I get a reply, and you say it's 100 milliseconds. I send another request, and again, 100 milliseconds later, I get another reply, right? Language designer said, okay, we're gonna help you. We will implement something what is called async. And it can be a language primitive, right? And what it will do is that the moment you send this, invoke this function, there will be something internal, like kind of like a yield method, which we discussed before, which says, okay, I know that I will be stuck forever. So please go ahead and dispatch the next iteration of a loop. So it's kind of like you create a tiny thread here, which executes this DNS lookup. And when it gets blocked, you go here to the async point and you start another thread, right? And that one gets blocked. This one will, like, you start a third one, right? And then maybe there will be like some kind of a do finish block, and where you say like these threads have to finish. But what will happen is that you will be able to quickly dispatch 3 requests to DNS server. You will wait for like roughly 100 milliseconds from like the beginning of the first one, and then 3 replies will come back. So the total direction of total length of a loop is shorter, right? And this primitive async, you can think of it as a coroutine. But there are different like ways how people use coroutines as well. Does it help? This example? Any questions about it? It's kind of intuitively, it's useful. It's like you say, I'm creating a very lightweight threads. They are so lightweight that I don't call a POSIX thread create. It's in the language. That helps.
What will be the difference between like a coroutine and like a future?
What is the future? I forgot. Future. I don't remember. So let's take it offline. I used to know, but since I got stuck with kernels, I don't use futures and I don't remember anymore. But I can look it up for you. Futures. No, I mean, let's talk offline. So, but it's a mechanism which allows you to capture your environment, and if I remember correctly, continue from it later. So it's like an example when it will be useful is, imagine you say, I'm building a web server, and request came, you run a function, and you say, look, by the way, I will send a reply, but I expect that the session will come back. And I think at this point you can create a future and say, I will continue from here. But again, I'm so naive that I can be even wrong.
So in C, would you call like pthread or something to make this?
No, that's the whole point. So to create this, you can just create a new stack and start running. In fact, this is possible in C with a macro. And ideally, you would like to have some language support, like the syntax will be cleaner, but you can build this with macros in C. I can point you to the implementation. And that's the point. That's why I was sorry, like for this kind of detourish, like whatever, part of the lecture. But the idea is that every time you create a thread of execution, you can just create a stack. And I'm saying that there might be multiple stacks, and your runtime you can play with them. So I'm just saying, again, it's a little hard to understand probably because there is no concrete example right now, but we'll get to it. But what I'm saying is that just keep in mind that the stack array is somewhat special. And as we go forward, okay, I promise I will introduce you to the idea of a thread and a process, right? And then you will understand, like if you later rewatch this lecture, you'll probably understand what I'm trying to say here a little bit better. Okay, so stack, area of memory, right? If I ask you a question, what's the main purpose for the stack? Why do we need it? So, okay, we're back on track. So people who were like, okay, man, like, stop this, I stopped. Why do we need stack? What's the main purpose? Someone should know, obviously. To do what?
Remove the function call. Just say pop function is completed and you need to come back to the earlier one calling function.
Right. So what you're trying to say is that stack is a mechanism which allows you to remember how to return from a function. Okay. It sounds a little bit cryptic, but let me give you an example. So normally you call a function foo, right? And that's okay. So inside foo, you will have return statement, right? The question is, what instruction you want to execute after this return statement, right? So you called foo here. Foo is implemented somewhere over here in the text of the program. Here's your return assembly ret instruction. The question is like, what's the value of instruction pointer after this instruction, right? And there is no like straightforward answer. So you say, maybe I can encode the address here, like set some kind of an address A. And this address A will be right here because logically you want to continue right here, right after you invoked function foo, right? So that's fine, seems to work. The problem comes with when you have multiple instances of call sites. So you invoke function foo from multiple places, right? So now you cannot say, okay, I want to return always to A, because maybe sometimes I return to A and sometimes I want to return to B, right? And so the question is, you need to remember this. When you do an invocation here, when you call a function, you say, I want to remember whether I want to return to A or to B, right? Is that clear, this motivation? And the question is where? You can say, maybe I can have a dedicated register, but you immediately say, well, what if I return, like invoke function 10 times recursively? Then you need to have 10 registers, maybe 100, then 100 registers. And so logical answer is that let's have a region of memory, which we will call a stack, right? And you can say, look, I will remember, when I call a function, I will remember A here. If I recursively inside foo will call it again, I will remember some kind of a C and C again and C again and C again. And when I start returning, I will be saying, okay, what's my return point? I will look at the stack, I say it's C, and then I will go to C, right? That's the main motivation. So, but also it helps you to allocate local variables because there will be instances of variables, and I will explain it in a second, right? So essentially, if I ask you again, your answer should be something like this. So stack contains information for how to return from a subroutine, right? Essentially. And again, you don't have to remember the specific way I phrased it. And I'm bad with phrasing things, right? So, but you need to remember this intuition. You just remember how to return, where to return from a function. Okay, so let's take a look at the example. So again, this is my address 0, so stack will be growing this way. This is current value of the instruction pointer. As you can imagine, there might be some information here as well, like maybe there is some data here, right? But the current value of the ESP register is pointing here. My instruction pointer points to a call instruction. So call instruction essentially is yet another assembly instruction which has a label as an argument. Label is foo. In practice, it's an address, right? And there are different encodings for those instructions. Sometimes it's an absolute address, like a real x8000 and so on. And sometimes it's a relative address, right? So sometimes it's also compilers can generate relative to the current value of the instruction pointer, right? So when the CPU executes this call instruction, what it does first, it pushes on a stack this label, this address A, right? Not label, address A. Address A is an instruction which follows the call instruction itself. And I said just a second ago that there are different ways to encode those addresses. So call instructions themselves on x86 are variable size. That's why instead of saying just +4 or something like that, like in MIPS, I say instruction pointer plus the size of the call instruction. Because maybe it's like 4 bytes, maybe it's 5 bytes, right? So it can vary. But this is the hardware itself says, okay, I got it. So this address A will be placed here, right? You get the point. So this is the address A, and this is the 4 bytes. It will be the address A here, right? Now what happens next? Since we're calling a function foo, the hardware will update the instruction pointer. First of all, it will update the stack pointer to say, okay, since I already used this location, my next available location on the stack is this one. So ESP will be pointing to this new location, right? And next, it will update the instruction pointer to the entry point of the function, right? So this is the label foo. It's like says, okay, EAP is pointing now here. And in the next iteration of this fetch, decode, execute loop, it will execute this instruction, right? Agree with this? The first instruction of a function foo. Any questions? What is that?
In stack, where are we placing the foo?
Label foo.
Yeah.
We don't.
But we mainly use for the function calls, right?
Right. So, and I'm calling a function right now. I don't need to, like, imagine this foo is an address B, right? This is B. I don't really, like, the only thing which I have to do is I have to make sure that EAP equals to B, right? Instruction pointer, because this is the next instruction which I will be executing. I don't have to remember anything that I'm executing B. I only have to remember that I have to come back to A, the instruction which follows the call instruction, because when I will do a return, I will come back to this instruction and continue my program from there, right?
What about the variable allocation?
We'll cover it in a second. So there will be variable allocation in a second.
I just have a quick question on the stack pointer. I always mixed up. So the byte that the stack pointer points to, is that part of the stack that's allocated or not?
So you're saying what you're asking is I think you're right, and my drawing is imprecise. I think it's actually the way it was. Let me just erase link. So the way my drawing goes is that the question is like whether this ESP points here or here. Can I again take it offline and clarify it later? So like it will become clear in a couple of slides most likely, but I don't remember right now.
Does the body just look at the top of the stack when you're talking to
Right, exactly. So what you're saying is that after the invocation, the A will be placed here and ESP will be pointing to A. So which means that it was pointing to whatever the location was here, right? So essentially, that's the answer, right? So is that what you asked, right? And that answers your question, but maybe I'm a little messy here. So the way the stack, so this error should point to here, and there is some data. Maybe it's like x55 right now. And I think what call does, it changes the stack pointer, decrementing it by 4, right? So it starts pointing here, and this is where it places the A errors, and it becomes at the current top of the stack. That's how it works. Sorry.
So what happens in async calls?
What happens is what?
In async calls,
Asynchronous. Let's come back to it later again. Maybe I will make it as a homework, and then you will, especially for the graduate class. Undergrads can do it as an extra credit, and graduate students will have to do it. Just, it will take us too far away from the main subject if we start talking about async. But it's very, very easy. The moment you understand this and how it works, you can build your own async runtime, no problems. Any other questions about like this invocation, especially undergrads? Because graduate students, they know how to, what is it? Comprehend knowledge by later on looking at books and whatnot, right? Because that's the main skill. But you guys, undergrads, you have to ask questions here. It will be easier for you later. All good? Okay, so we started executing foo function. It will contain some instructions, right? So machine will execute them. At some point, you reach the ret instruction. That's an instruction, again, assembly instruction on x86, which returns from a function call. So what it does, because remember, it doesn't take an address, right? So you don't know where to return. But the semantics is following, that it will take the value, which is currently pointed by the ESP register. And this value will be A, which we placed when we placed on the stack. It's essentially the address which points to this next instruction after the call, right? That was our A. And it will get this value. It will decrement. It will essentially set the EAP pointer to point to this value. And it will decrement, or in our case, increment, because it will be, this is the max address. So ESP will get the value of ESP plus 4, right? And it will be pointing here. That's the state of your machine after you return from a function. Agree? The stack memory itself, if you had a value A here, the value A remains. Like, it doesn't get erased with zeros or anything. It's just a memory. A still is there. It's just that the top of a stack points to the next 4 bytes, right? And whatever is there, we don't know. We don't really care. So maybe we're calling another function and it's another return address. Maybe it's a local variable, which I explain later, but something is there. But after that, we can continue executing a function, right? Here. Or not a function, but our main program, right? Agree? That's how function invocations works. So let me just introduce those instructions again. So call instruction, it essentially an unconditional jump. It always jumps. And the semantics is the following. So you push the current value of the instruction pointer plus the size of the current call instruction on the stack. Okay, what is push? We'll soon cover it. It's an instruction which places something on a stack and changes the value of the stack pointer. And it jumps to the label, like this label, my function. Right? And the ret instruction essentially pops an address and jumps to that address. Okay, I kind of like, my flow in the slides is broken. So because I said, okay, I introduced push and pop, let me introduce them in a second, right? So there are some other, there are some other uses of the stack, right? And some of you were jumping ahead, right? So stack can be used to allocate local variables. It can be used to pass parameters into the function. And sometimes you run out of registers and you have to save intermediate results on a stack, right? And compiler will generate the code to do that, right? But okay, let's go step by step. Again, as I was saying, I introduced these 2 instructions. One is push, one is pop, right? So the 2 instructions which allow you to explicitly manipulate the stack, right? So what push does is the following. So if this is your state, and again, stack 0 is here, max address is at the bottom. if you're executing a push instruction which takes a constant like bar and current value of the ESP pointing here, then the push will subtract from 4 from the ESP, essentially making ESP to point here, and place the value, this bar, into this cell and move to the next instruction, right? So this is how your stack will look after invocation of a push, right? So effectively what happened is you saved something on a stack with an instruction, and you can do it multiple times in a loop. For example, you can keep pushing bar, right? And then bar will be showing up here, here, and so on, right? And the stack pointer will always be like growing downwards, right? Right? And this doesn't have to be a constant. You can push a register. So you can say push EAX. And essentially it says that I saved intermediate value of EAX into this memory, which is pointed by the ESP register, right? And you can do it again recursively. And a symmetric function to push is pop. So essentially, if you do something like, this is the state of your program right now, it points to the bar on a stack. If you say pop EAX, the value of bar will be placed into the EAX register, and the stack pointer will be incremented by 4, right? So it will go to the next instruction. Again, ESP is incremented by 4 because this was some value A, and this is A plus 4, the address, right? And the value of EAX gets bar, right? You restore that value from the intermediate memory. Any questions about it? So we have like 2 instructions which explicitly manipulate stack, push pop. We have a call instruction which implicitly does it, uses the stack to remember the return point. And then we have a ret instruction which essentially reads this saved return address and just essentially jumps to it, right? You can abuse that, and you can actually, as I said, you don't always have to use push and pop instructions. You can do something like move and use ESP as a memory pointer and just say X bar, right? And you can say, by the way, since I did it, and I can just do sub ESP 4. So I decremented ESP, right? So that's also legal. So you can do it yourself, or compiler can generate this code. It's fine. It's the same as, this is effectively the same as push. They agree?
Is the bar an address then, or is just?
No, it's a constant, right?
Okay.
It's in our example specifically, it can be any constant, right? It can be an address, it can be anything. It could be value of, of your index in the array or something, anything what you use right now, right? But it's a constant. Okay, got the stack, right? So this is actually the end of the previous lecture. And right now we understand how stack works. We kind of understand how function invocations work, right? But let's go through more concrete examples, and specifically, let's go through this idea of a set of conventions which allow us to invoke functions, right? So that's like beginning of our today's lecture. Let's start here. So since usually it sometimes starts on a new day, this is the recap, high-level overview. We have all of this. We already know it. We just did it. So here, what I do is I go through an example. I draw a stack. Let's, for simplicity, draw it in such a manner that this is 0 and this is a max address, right? And imagine your stack pointer ESP is currently somewhere here. Imagine you invoke this foo, right? And this is the label A, immediately after the invocation of a function foo, right? So when you invoke it, passing 4 as an argument, what happens is that this A gets placed on a stack, right? And stack points right here. You get to this line, you check if A is 0, A is 4, right? And you invoke a function, you decrement A and invoke foo with 3, right? So imagine that this address is B, right? So when you invoke a function foo here, this B gets placed on the stack, right? And you again jump, since you called the foo, you jump here, but now A is 3, right? So again, A is not 0, you decrement A becomes 2, right? You again invoke foo, since this is the return point, B gets placed on the stack, right? You end up executing here again. A is at this point is 2, A is not 0, A, you decrement A, invoke A with 1, right? Again, B gets placed on the stack, right? You enter foo here, A is 1, it's not 0, you decrement A, you invoke foo with 0, right? And again, B gets placed on a stack. And this is your current value of the ESP pointer. Now you're inside this function, foo, with A equals to 0, right? So you say, okay, A is equal to 0, so I will execute this return statement, which gets compiled to this ret instruction. Ret instruction does what? It looks up the current label on the top of the stack and jumps to it, right? Okay, sure. So ESP gets changed to here. Instruction pointer gets changed to here, right? You're again executing this ret instruction. Question? Yeah.
In this case, would A or 4 be pushed onto the stack and pop every time you're checking it?
Can you ask this again?
So in this case, with foo equal 4, would you pop or push 4 onto the stack and then pop it when you're checking it inside the function?
What you're asking is, how do we pass this 4 inside the function, right? Where is this A?
Yeah.
We'll touch on it in a second. Just bear with me. So there are different calling conventions. Sometimes you pass those in registers. In the system which we consider x86 32-bit, we will be pushing 4 in the stack. For simplicity of the argument, and you're right, so that's what I got it. You wanted to point out, so you have to push 4. But on 64-bit version of x86, you actually can pass A in a register, right? That's why I didn't want to confuse you, but you're right. Okay. But let's get back to it in a second, right? So you again find yourself on this B label, and you again, B address, you again executing ret instruction, which again changes the ESP to point here. Again, you're executing your ret. Here, again, you're executing the ret because you find yourself at B. And at this point, since A is at the very top, you essentially say, okay, I got it. So I got to A, and you return, finally, you return here, and you will continue execution here, right? So is this, I mean, again, there's a lot of details, and it looks very, very easy on the surface, but we will take a look at concrete examples. We'll take a look in homeworks at analysis of the stack. But if you have questions about this, it's time to ask.
We're pushing the B value there, so that is common. I mean, the value will be same for all of the records, right? We push 3 B's, right?
Right.
So the address will be the same for all of them, right?
The address will be the same, right? It's the same B, because this is where B is, right? And this is where you called foo, right? 4 times. And you will be returning 4 times to the instruction after the call function, right? And this will be a stack of your, state of your stack, right? Any other questions? Okay. So, okay, we went through an example, and now the question is, what are those calling conventions? And calling conventions kind of relates to your question, right? Our goal is to build composable programs which allow recursive invocations, meaning that maybe you wrote the main function, you call printf, and someone else wrote printf. You need a convention of how you're gonna invoke printf from your program, right? And it's a little bit like there is a step which is called compiling and a step which is called linking and loading. We'll go through them next week. But okay, nevertheless, you can kind of feel the need for a convention which will describe specifically how to pass arguments, like we called foo and we passed for. Where is this for? Is it in a register or is it on a stack? How to return values, so maybe if we return something like assigns it to n, for example, right? So where is this, like, return value? Again, it can be on the stack or in registers, right? And sometimes you you make different choices, and these conventions will differ from the compiler. Sometimes optimizations, no, typically not, because optimizations are orthogonal to the convention, but essentially from the compiler architecture on which you're executing it and stuff like that, right? Even between 32-bit and 64-bit version of x86, the convention is slightly different, and I will highlight the differences. Okay, so the first idea which is there is to maintain the stack as frames. Strictly speaking, it's not needed, but we'll discuss a little bit later why it's useful. It's useful for debugging, and that's why we kind of explain it, and you will see it in real programs as well. So how does it work? So imagine you have a function draw square which calls another function draw line. We say that we will designate portions of the stack and we'll call them a frame. So this blue area of a stack belongs to draw square. When the draw square calls draw line, we will, roughly speaking, move to a new section of a stack, which we will call a frame, right? And the organization of a stack will look like this. So there will be a return address, there will be a pointer, a special register, a bottom or a frame pointer or a bottom pointer, which points to this value, to this location on stack. And parameters which we pass to the draw line will be here, and the local variables which we allocate inside the draw line will be here, right? Again, does it help you much? I bet it does not, right? But let's just break it step by step. So what we're gonna do inside every function, and it's a convention, like it's if you write a function by hand, you can break a convention, maybe stuff will stop working, right? But essentially you say, if my compiler follows this convention, it will generate two sequences of instruction. One is called a prologue, and one is called an epilogue. So a prologue is the sequence of these two instructions, which are executed when you enter the function, right? Remember, I said that we will dedicate a special register, EBP. I mean, I say special, but it can be any register, to be honest. So x86 chooses EBP. And it saves the old previous value of EBP on a stack and initializes the current value of EBP with the stack pointer, right? So it's essentially current value of the stack pointer gets saved here, right? Which means that if your stack, if you have some value of the EBP, it points somewhere over here. You were running something, the stack was growing, so you were saving something on a stack. And you suddenly enter this function. So this old value of the EBP gets saved from the stack here, right? And the value of the ESP will be pointing to this current location of a stack, which allows you to build a chain. So kind of like you know that this EBP points to here, and somewhere here there will be saved another version of the EBP, which will point to the previous frame, right? And right before leaving the function, you say, look, since I know that at the very top of the stack, there will be first the return value and then the EBP, you pop EBP, saying just essentially save that in the EBP register and call the read instruction, right? Again, a little bit confusing, mildly, but it will become clear in a second. But what it allows you to do is essentially this diagram. So you say, look, my EBP points here, right where the return address is, right? I save the old value of the EBP here. And this old value is actually pointing to here, right? We'll see why it's useful. It's useful to do, essentially, if you're doing a recursive invocation and you crash in a function, your debugger or you as a human can walk the EBP pointer and essentially say, okay, look, I will generate a stack trace. Essentially, you will know that you got called from main called foo called bar called boss, and you crashed inside boss, right? Okay, bear with me for a second. So stack frames, right? So the question is, what about local variables? Someone was asking. Again, let's take this tiny detour. The question is, what types of variables do you guys know? I was asking it last time, but probably the memory is still fresh. So who can tell me? It's kind of useful, and it's a little bit of a detour, but still. So what are those? Global, right? What else? Local, and what? Dynamic. And let's go through some examples to just understand them. So literally, why it matters is just that the place where those local variables and global variables are allocated, right? So global variables, remember, we did the assembly and we did this directives which allow us to allocate a sequence of bytes. So they go into the data section, or sometimes if they are not initialized, to a subset of a data section, which is called or better safe space, BSS, right? Dynamic variables are allocated on a heap, and local variables are allocated on a stack. Again, if I say this, it doesn't probably mean much, but here's a couple of examples from the C language. So imagine you have a C program. If you define a variable or declare a variable in a global scope, right? So this is an array of characters, hello. This gets allocated, this is a global variable, and it gets allocated in a data section. Agree? C is a funky language, so it has this static specifier. And despite the fact that this variable is declared in the local scope of a function foo or a function main, because of the static specifier, it also is placed in a global section. So effectively, like there will be hello, right? With a 0 at the end. And maybe next to it, there will be world allocated in this data section, right? Agree? Just because it's static. So those are global variables in a C language. However, if you drop this static with a type and then a name, so in this example, this is the world, and this is oh man. Oh, actually, I'm sorry. Talking about dynamic variables, sorry. So let's just concentrate for a second. For a second, let's concentrate on this one, bold line. So this variable is allocated with the malloc function, right? So this is called a dynamic variable, right? So who can tell me what's going on underneath? What happens when you call malloc?
On the point in memory that it returns a pointer that
Correct. So imagine this is your memory. Imagine maybe somewhere here your stack lives. We don't really know where it is, but it's here. Somewhere here, maybe your data section lives, right? Maybe somewhere here, the text of the program lives. So it's your code here, right? Or text. So this instruction, like which calls malloc, this call lives here, right? this global hello lives here, right? And this area, imagine the runtime of the language and the operating system say this is heap. malloc is a library function, which essentially tracks the status of this heap. So the simplest memory allocator can be something like just a bitmap somewhere over here, which says, okay, if this bit is not set, then this byte is empty, right? And you can do a scan through the bitmap and say, look, if I want to allocate 64 bytes, I need to find 64 consecutive bytes which are not allocated, right? This is heap. And return the pointer. So this is essentially becomes a pointer, and this is where you will have your 64 bytes, right? You can imagine that you can do more sophisticated tricks. You can maintain, instead of using a bitmap, because bitmap is a linear scan, you can say, well, I will maintain it as a linked list of 3 regions. We'll come back to it and we will build malloc later. But you get the point. So these 64 bytes are allocated here on a heap, right? And you can allocate them dynamically, and they can outlive the lifetime of a function, meaning that if you allocate and never deallocate this memory, then it will stay there like allocated. The malloc library will believe that this memory is occupied, right? And it's called the memory leak, typically, right? Got this point. And finally, what we need to understand is local variables. As I was saying, if you drop this static specifier, then this variable world, which is an array, will be allocated on a stack. So remember my picture here. So you have data section, code section, heap, and the stack itself. So that world, which is here as well, will be allocated here, right? I will ask you a question. So why are we going into those complexities? So it seems non-trivial. So like 3 different allocation sites. Why? Anyone has an idea?
In case of a function call, right? Maybe the stack space might not be available, so we will be having very limited space. So in that case, we might need extra space to store the data. So that's why we need a heap.
Okay, so what you're saying is that if we want something large, we want to allocate it on a heap, right? And this is kind of how people get taught programming, right? You say, look, large variables don't allocate on a stack because stack is limited. In fact, this is kind of wrong because it depends on the runtime. And there are some languages which implement infinite stack. You're right, it's a practical rule of thumb, but the real reason why you allocate something on a heap is different. So what is this real reason? Why would you allocate something on a heap versus on a stack?
So then space even when it goes out.
Exactly. So what your classmate is saying is that local variables get deallocated after the function finishes, right? But imagine you allocate an object here in function foo, and you want to have it later here when you invoke a function bar. That's why you allocate on a heap, because it outlives the scope of a function or a lifetime of a function. And that's the main reason for the heap, right? And the main reason for the heap versus the data section is that data section is fixed. Essentially, it's generated by the compiler statically, and then you have to guess how many objects you need upfront. But with the heap, you say it's dynamic, and you can say, well, I don't know why. Maybe you're processing a large graph. You program like maybe counts nodes in the graph, but you don't know the input. Maybe you read it from a file or from the network. You don't know how many nodes you will have, 100? Because otherwise you would say, okay, my graph here will have 100 elements. But you say, oh, well, that's okay, but maybe it's 1 million, maybe it's 2 million, right? And that's why you try to allocate them dynamically on a heap. But the main reason local versus heap is that is a lifetime. But you're also right that in most practical scenarios, the memory of the stack is limited, maybe to something like 64 kilobytes. And people said, okay, for practical purposes, let's keep the stack small, and then allocate large objects on the heap as well. So in practice, you will have, even if you don't need the variable to exist after the function finishes, you still will have to allocate it on a stack for practical purposes.
For arrays in the data section of the global scope, would they need to store a pointer in the data section and the comments to the array?
So the question you're asking is, what is really, I didn't want to lose this drawing. Like, what is really happening here, right? Right, so we know that this, or like, even if it's a static, that's what you wanted?
Yeah, it's static.
Yeah. So we know that the world is in a data section, right? So imagine this is our data section. And world sits here, right? And there is a 0 here. The question is like, what about this part? What is it? Is it a location, like, is it location on the stack? Or maybe it's just a register, because the compiler is so smart that it says, okay, look, literally what you need here is a kind of a pointer to world, right? You need this address of world. But I don't think it's defined by the C language. So it may be on a stack, or it may be immediately in a register. And in most cases, it will be in a register, because compiler will try to optimize and will just load this variable as a constant into the register. So you will not even have a space allocated, right? But in our class, we can say that this location which holds this pointer will actually be allocated on a stack, right? And so this pointer, which points right here, will be allocated on the stack as a local variable.
Yeah, because I was just wondering, like, imagine in the future I said world equals something else, or like the hello equals another array, and it's a global. So we have to update or whatever for that other global. Or I can make that.
It's probably interesting, but let's keep going. What you probably, okay, this is useful. So we'll come back and I will like show you a real example later maybe. But let's just understand, okay, one thing about local variables, which is our current kind of subject, right? So this specific variable world is allocated on a stack because it doesn't have the static specifier here, right? So the question is like, again, why do we need these local variables, right? In the first place, it's a very useful thing, because imagine we have a function foo, which has some local variables here. And you can say, okay, where's this memory? Because especially if foo calls itself recursively, each instance of this foo will need its own version of A, B, and C, right? Because in the first instance, it may be like equals to 5. In the second, it will be equal to 6, right? So that's why essentially every time we invoke a function and it has some local variables, we'll allocate them on a stack. So essentially those A, B, and C will be sitting on a stack for the first invocation of foo. When the foo invokes itself recursively, it will allocate again A, B, and C on a stack as well, right? And maybe this A will be 6, and maybe this A will be 7, right? And we saw it just a second ago when we were invoking foo with 4 and then 3 and 5. And I said, okay, I don't really know where this integer or this argument is, but it's actually on a stack, right? But it was actually like not a local variable. Okay, so a concrete example. So how do we allocate space for local variables? Imagine you have a function, you say a type int, so it's 4 bytes. You have 3 variables, A, B, and C. And I just said that we want to allocate them on a stack. So what do you think how this allocation will look like in terms of assembly language? What kind of code the compiler has to generate to make sure that there is space for those variables?
Does you have to adjust the stack pointer by default?
Exactly. So you just adjust the stack pointer by 12. So again, you have a my function. Remember, we maintain the stack frame, so we have a prologue and the epilogue here, right? But you say, look, I will allocate some number of bytes on a stack by subtracting them from the stack pointer. Why subtracting? Because the stack grows downward, right? So if this is your value of the ESP, this is 0, you say I want 12 bytes, so essentially you subtract 12 here. And this is the space for A, B, and C, right? You allocate space for them on a stack. Of course, like since you adjusted the stack pointer, you will not be able to correctly execute the epilogue, right? You will not be able to return from a function. So because your return value is somewhere over here, right? Agree with this? Or to be more specific, there will be a value of a bottom pointer and a value of the return pointer on the stack, right? And really to execute this ret instruction, at this point, you want the ESP to point to this, right, address. So you have to restore the original value of the ESP, which was there when you entered the function. And luckily you have it around. So you have it in the bottom pointer. I mean, you can generate this sequence differently. You can say add ESP, same number of local bytes, right? And that's okay. That's one way to do this. And that actually happens in practice as well. But since you already have the value of the ESP saved in the EBP, you just load it back into the ESP, right? Kind of like deallocating this space on a stack. Agree with this? Okay. Here is an example. So again, same example. So you use your function, right? You first maintain the stack, the stack frame, saving the old value of the EBP because it's the value in the register. So you push it on a stack. You initialize the new value of the frame pointer by loading ESP into the EBP. You say, okay, I'll reserve 12 bytes on a stack by subtracting 12 from the ESP register. And then you can initialize those variables. So do something with them, right? So you say, my location of a, remember, like, again, this is how we entered the function. So there will be a ret code here, return address, this labels like A, right, return address. There, since we pushed EBP, the old EBP will be sitting here. And then since this is 0 and we allocated, our current value of EBP is actually pointing right here, right? Our current value of ESP is pointing right here because we reserved space for 3 variables, right? And that will be like A, B, and C. And this is how we can access them. We say EBP minus 4, this cell is A. And if we initialize here A equals to 10, sorry, then this is replacing 10 here. EBP minus 8, this location of B, we'll place 5 here. And EBP minus 12 is essentially this one. The value, the location for C, we'll place 2 here, right? That's the layout of your stack when you, after you executed those functions, or those instructions, right? Any questions about it?
I'm just curious, is there a way in assembly to use like variable names for those instead of just using like EBP minus 4, for example?
Most assembly languages support some kind of a macro language. You can define a macro, say EBP minus 4, which will probably resolve to this, but I'm not an expert. Most likely you can. Any other questions? Okay, let's keep going. A little bit hard. So the next question we have to, so we got the point how we allocate local variables, right? And essentially if we call this function, my function here again, recursively, the same will happen. There will be some kind of a return address here on the stack. Since we execute this value of the EBP, like imagine it's like, I don't know, 80010010, right? This value, this is the address, will get pushed here, 80010010, right? And again, we will do the same exercise. There will be same versions of A, B, and C, 10, 5, and 2, right? And maybe the function will be changing them, right? But essentially, we have 2 instances, right? For each invocation, there will be its own private instance of this variable, right? Now the question is like, how do we pass arguments? Remember, this is the question which you asked before. When we invoke something like this, foo4, where is this 4? And you have options, as I was saying. You can either pass them in registers, or you can pass them on a stack, or maybe you can pass some number of arguments in registers and the rest on a stack, right? And all of these are real, right? So since we're looking at the 32-bit version of x86 assembly, it says that the calling convention is following. You pass all arguments on the stack. You pass return values in 2 registers, EAX and EDX. So typically when you do a value 0, the 0 will be placed inside the EAX register. And there is some specific case, which I don't even remember, but at some point you use the second EDX register to pass something else. And does anyone remember? No? Okay, we'll come back to it. x86 is a little bit different. x86 64-bit. You pass the first 6 arguments in registers, and this is the sequence. First goes into RDI, second goes in the register RSI, RDX, RCX, R8, and R9, and the rest are on the stack. And the return value is again in these 2 registers, RAX and RDX, right? Why is it done this way? Because x86 has more registers, and so if you already have a variable in register, you don't have to push it on a stack and pop it from the stack again inside the function. It can just stay in a register, so the code gets a little bit faster. But on 32-bit version of x86, we pass all arguments on the stack. Let's take a look at how it's done. So again, my function, you say 3 variables, you're passing x, y, and z. And this is the invocation side. You specifically invoke it with 2, 5, and 10, right? So literally, the compiler will generate this code. And this first argument will be the closest to the invocation side. So you push 10 on a stack, the last argument, you push 5 on a stack, and you push 2 on a stack. And then you invoke a function. So in our previous example, when we were invoking foo of 4, how will the call side look? What's here?
Would be push 4.
No, push 4 will be here, right? Or 4, right? So the person who was asking, did we push 4 on a stack? Yes, we did. In this specific, in case of 32-bit version, we do push on a stack. So, and then if you are inside the function, this is how your stack will look like. Remember, we pushed 10 on a stack, we then pushed 5, we then pushed 2, then we did the call, right? So this is how it looked like. Push 10, push 5, push 2, then we did a call. The call instruction places the return address on the stack, right? So this return address will go on a stack here, right? Then, since we maintain the frame pointer, we push the old value of the EBP on a stack. And then if we allocate in local variables, there will be down the stack, right? So essentially, this is address 0. This is how the stack was growing, right? So if you're running inside the function somewhere, you know that, okay, your EBP pointer points right here, right? EBP plus 4 will be a return address. EBP plus 8 will be your first argument. EBP plus 12, your second argument. EBP plus 16, your third argument. And EBP minus 4 is your first local variable, right? Agree? That's just a convention, but okay. They said, okay, now you can give me a library which implements foo, and I will call it from anywhere, just because I know that it takes 1 argument, so I will have to push 1 argument on the stack and then invoke it with a call function. Let's take a look at the example. So again, this is a function caller, takes no arguments, void, right? It still nevertheless manages its own stack frame, pushes the EBP on a stack, initializes the current version of a stack frame with the current value of the ESP. Since we are trying to invoke a callee function with 3 arguments, 1, 2, and 3, we'll push those arguments on the stack in this reverse order, like 3, and then 2, and then 1. Then we call a subroutine callee with the call instruction, right? It does something, right? Since we allocated space for local variables, where did we allocate this? What are we doing here in this line? We didn't have local variables, so why did we do this? The comment tells us these 3 instructions change the stack, right? So we push 3, 2, and 1. So the compiler has to say, like, forget about those 3, 2, and 1. So we add the value of the ESP back. Is it clear? We use the subroutine result. Remember, this red will be returned in the EAX register calling convention. We just covered it. So we say return red plus 5. This is the code which compiler generates. It adds 5 to EAX. We do the epilogue. We restore the old call frame, right? The one which we pushed here, right? And then we do this return, right? I will ask you a question. Where is this red? Because we're returning a value, return red. So, but we don't see an instruction here which does anything like that here. Exactly. So compiler was smart enough, since it's already in the EAX, you can just say, I will leave it there. It's already ready for return. If this, like, if it would be a different variable, like if you were returning maybe like, I don't know, something like int a, and you would have something like a equals red plus 5, and the compiler is not smart enough to place a in the EAX, but place it into something like EBX, then you would do something like move EBX into EAX, right, to make sure that you're returning what you need to return, right? Again, and this is a real, like, next time we will take a look at real examples of assembly code, but this is pretty real. So this is what your compiler will generate underneath for this C function, right? And again, let's take a look at another example, like, pretty much been here before. So again, this is the same example, but the question is like, what is inside this callee, which received these 1, 2, 3 arguments, right? So imagine this callee has 3 variables, A, B, and C. We again allocate space on the stack by subtracting 12, right? Then if we want to access those variables, remember the layout of the stack. So the arguments will be EBP plus 8, EBP plus 12, EBP plus 16. Or you can also like access them relative to the stack itself, right? Because you know the value of ESP. So it's either EBP minus 4 or ESP plus 8, just because this is how the addressing works. And you will do something at the very end. You will deallocate the variables by moving the value of the EBP back into the ESP, restore the stack frame by popping EBP and returning, because at this point, at the very top of the stack, there will be a return address. Okay? x86 has a special instruction for performing this sequence of operations. It's called leave. So essentially, if you see leave, that's essentially just the same as this. I never see it in practice because compilers don't always maintain the stack frame, and leave is effectively almost never seen, but just heads up. And let's come back. Okay, I started with the stack frames, and it wasn't really ever clear, why do we really need them? Right, because it seems like a little bit unnecessary. We push one register when we enter the function, and we pop it back. It allows you like to do something, but what is that something? Let's spend this last 3 minutes to understand what it is. So why do we need the stack frames? What are the ideas? Any?
Debugging.
Debugging, yeah. So explain, how do we use stack frame for debugging?
You can see the backtrace of the function call.
That's correct. So there are two main reasons. And the answer is, to begin with, they are not strictly required. For example, a GCC compiler option flag emit frame pointer can disable them, right? So if you pass this flag to the compiler will not generate the stack frame. And this is the explanation from the GNU documentation for this flag. Don't keep the frame pointer in a register for functions that don't need one. This avoids the instructions to save, set up, and restore frame pointers. It also makes extra register available because EBP is now a free register, right? You can use it in all arithmetic operations. But it also makes debugging impossible on some machines. So why? Why it becomes suddenly harder without the stack frame?
Yes, because the OS just not give you access to like we got memory outside of the stack.
No. Let me explain it like this. So if you don't have a stack frame, imagine you have just something allocated on a stack, which when you enter the function, ESP was here, so this one was ESP plus 4. Maybe it's your argument, right? So if you want to access this, you have to generate an instruction which says ESP plus 4. Imagine you move through your function. You go through some if then else statements, for loops, and you maybe allocate some additional variable in a stack. Maybe you just have an inner scope and there is another integer, right? So suddenly, the address of this parameter is no longer ESP plus 4, but in that part of the code where you're using that additional thing on the stack, it becomes ESP plus 8. If you're smart enough, you actually can keep track of this, right? So, but you have to be smart. And it's easy for the compiler. Compiler can just account for that and say, look, I allocated this variable, so in this part of the code, it will be ESP plus 8. Later on, I deallocated it, and it will be again ESP plus 4. It's a little bit hard for human, but possible, right? But it complicates your role as a developer. So if you want to look at the code of a function and say, okay, for example, you're debugging a function, you don't know the source code. You're looking at the code and you say, what is this like? I'm accessing ESP plus 4, and later I'm accessing ESP plus 8. Is it the same variable or not? So you kind of have to execute the function in your head to understand that, okay, allocation happened, and right now it's the same variable, right? So compiler can help you. When you have a debugger, it will generate something what is called debug information, which will maintain this mapping for you. And if you have a debugger, it will show you, okay, it's the same variable. If you don't have this debug information and you as a like a OS developer just look at the source of the machine code of the function, it's very hard, right? And moreover, like you said, it's hard to unwind the stack in case of a crash to print the backtrace. So what is this backtrace? Just give me a second. So remember, imagine we were in main. Main has if, it invoked bar, and in else, it invoked maybe bar as well. And bar itself maybe invoked bus, right? And you crash inside bus. Your stack, you have ESP. If you don't have a frame pointer, you don't really know whether you got invoked from here or from here, right? It's there, this address A or B, it will be somewhere on a stack, right? So like it will save A or B. But you as a human, it's very hard to reason about it. However, if you have a stack frame, the stack frame will be pointing to a specific location, which will maintain, and right above this location, there will be A, right? Because you know that the moment you, like the current value of EBP points to the old value of EBP, right? And right above it is the return address, right? So you can say, okay, I know where it is, So by looking at the current value of the EBP register, you first understand where you got invoked from, and you can actually walk this chain. You say, look, there will be another EBP, and there will be another address B here, and that's another return address, right? And you can essentially, by looking, like doing that in your head or with your debugger, you can say, okay, I was invoked from main, and then like bar, and then boss, and so on, right? And so if you crush inside boss, you at least know which functions were invoked before. It's called the stack trace, right? Again, compiler can generate this if you have debug info. If you don't have it, then you have to do it manually as a human. And in this class, we will have debug info, but there will be not enough support for this. So essentially, our operating system, the code which we will generate, will maintain the stack frame for you to make sure that it's easier to understand what's going on. So that's essentially what's happening. Okay, let's stop here, and we will quickly finish and move on forward next time.
So when will the homework 2 be released?
Oh yeah, we have to start working on it.
So yeah, I can fix it, and but when? Like
Maybe even like Friday.
tomorrow?
If we can, if we have time to do it until tomorrow.
I think I just need to fix the open laptop and
Yeah.
and it's ready to go.
I forgot. Yeah, I had a deadline yesterday, and I forgot to mention. Let me just quickly stop the recording here.
Okay.
How do we do this?